Good afternoon, everyone. Welcome to the Georgia Tech Manufacturing Institute's Lunch and Learn seminar series. My name is Paige Shee. I'm the Strategic Partners Officer for the Georgia Tech Manufacturing Institute, or GTMI. I'm pleased to co-host this series along with my colleague, Dr. Billy D. Brown, who heads up GTMI's Education and Workforce Development activities. GTMI is one of 10 Georgia Tech interdisciplinary research institutes that uniquely focuses on manufacturing research, development, and deployment. We tackle the grand challenges of today's manufacturers and help our partners move innovations from the lab to the market. GTMI has a wide array of facilities and equipment located both on main campus for basic research and nearby on 14th Street for applied research in the Advanced Manufacturing Pilot Facility, also known as AMPF. GTMI's mission includes education and workforce training, collaborative partnerships with industry, academia, and government, as well as thought leadership. GTMI hosts this Lunch and Learn series each fall and spring semester. Sessions are held every Monday at noon as live online events. These sessions are excellent opportunities for Georgia Tech faculty, students, and researchers, as well as our global manufacturing community, to learn and share advanced manufacturing knowledge. To ensure a seamless presentation experience today, all audience members are automatically muted. However, you have the ability to communicate with myself and our speakers through the Q&A panel on your screen, as well as the chat box on your screen. And we encourage you to submit any questions you may have for today's speakers as they come to mind. And then we will cycle through those at the end of the presentation so you can hear the thoughts from the speakers. In addition, we are offering a survey and would encourage all of our participants to take just a couple minutes to complete a brief survey and let us know what you thought about today's presentation and give your thoughts on what topics you'd like to see in future presentations like this. So today I'm very pleased to introduce Frank Henning and Holly Schors-Alles from the Fraunhofer-Gesellschaft Institutes in Germany, who will present applied research for vehicle lightweighting by Composites technologies and provide an overview of the Fraunhofer Institutes. Frank Henning will be presenting automotive lightweighting utilizing composite technologies. This presentation will give an introduction to vehicle lightweighting utilizing composite technologies by a holistic methods, material, process approach developed by the Fraunhofer ICT together with partners from KIT. Holly Schors-Alles will present the Fraunhofer-Gesellschaft, headquartered in Germany, is the world's leading applied research organization with its focus on developing key technologies that are vital for the future and enabling the commercial exploitation of this work by business and industry. Fraunhofer plays a central role in the innovation process. Professor Dr. Frank Henning is director of Fraunhofer ICT, which is one of the Fraunhofer Institutes, and has been a fellow of the Society for Advanced Materials and Process Engineering since 2020, as well as a fellow in the Society of Plastic Engineers since 2013. Since 2016, he has been managing director of the Fraunhofer Project Center for Composites Manufacturing at UNIST in Ulsan, Korea. And since 2011, he has been managing director of the Fraunhofer Project Center for Composites Research at Western University in London, Ontario, Canada. Since 2010, Henning has been an adjunct research professor in the Department of Mechanical and Materials Engineering, Faculty of Engineering at the University of Western Ontario in Canada. Since 2008, Henning has been appointed as full professor for lightweight technologies at Karlsruhe Institute of Technology, KIT, Germany. Henning is president of SAMPE Germany since 2016. Henning holds a PhD in mechanical engineering with a focus on materials and composites from the University of Stuttgart in Germany, earned in 2001. He earned his diploma in mechanical engineering from the same university in 1996. Holly Schors-Alles is the USA liaison at the headquarters of Fraunhofer-Gesellschaft in Munich. With over 20 years of Fraunhofer experience, including at a Fraunhofer Research Institute and the Central Administration, she supports Fraunhofer's activities with U.S. partners and oversees the foreign Fraunhofer affiliate, Fraunhofer USA, Inc. Thank you so much, Frank and Holly, for agreeing to deliver this presentation today. It'll be interesting to hear possibly some analogies between your institutes and what we have here in the United States, known as the Manufacturing USA Institutes. At this time, it's my pleasure to turn the presentation over to Holly Schors-Alles to begin today's presentation.
Okay. Thank you very much, Paige, for that very nice introduction. And thank you both to Billy D and Paige for this opportunity to be here for this series. So as Paige mentioned, I'm going to begin today with a short overview of what Fraunhofer is, how we work, what our goals are, and give you a very, very general overview of some of the research areas that we work in. So first of all, Fraunhofer-Gesellschaft at a glance. Although Fraunhofer is a household name here in Germany, it's a word less known in the United States. So I think it's important just to tell you where it comes from. Our namesake is Joseph von Fraunhofer. He was a 19th century researcher, inventor, and entrepreneur. As a researcher, he discovered the Fraunhofer lines in the solar spectrum. From this, he actually created methods for lenses to manufacture them, and then he owned his own his workshop, glass works, where he actually produced it. And this really sums up what Fraunhofer does. We research, we create products and services, and to turn that into commercialization. Fraunhofer-Gesellschaft was founded in 1949, and in those over 70 years, we have gotten to a point that we are now at over 30,000 employees in Germany alone. These 30,000 employees are spread out across 76 individual Fraunhofer institutes in Germany, many of which have multiple locations. Last year, we had a total business volume of 2.9 billion euros. And as Paige mentioned in her introduction, our entire mission is to do research and research and development to benefit society. And we do this in practically every areas of research that exist, and we are a nonprofit organization. Any surpluses that are acquired by the institutes through their work is funneled back into the research activities, and so we are purely service-based society for Germany, Europe, and the world at large. Where do we fit in the German research landscape? Here I have an overview of kind of the biggest names of research and technology organizations in addition to universities. At the bottom, we have the Max Planck Institute, which focuses on basic research. Then we have the Leibniz Gemeinschaft, which has a very strong focus also on culture, social sciences, and education. They're slightly more knowledge and application-oriented basic research. Then we go slightly more into the green area, Helmholtz-Gemeinschaft, which has very large-scale research projects, facilities. They work a lot in infrastructure programs. They do topics such as particle physics, astronomy, large computer HPC clusters, climate simulations, etc. Then we have universities, which are kind of in between basic research. They also have their foot in applied research as well. We have over 400 in Germany. And then Fraunhofer, which is dedicated exclusively to applied research. So we are all the way in the green area. Fraunhofer has a very unique role in this capacity. We kind of have one hand in basic research and the other hand with industry. So we are kind of the translator. We take what comes out of universities in their basic research. We figure it out how it can be turned into a very marketable product or service, and we find the appropriate customers who can commercialize this. As a result, it's crucial for all of our institutes to have a very, very strong link to academia. And for this reason, Fraunhofer has really a mandatory model that the heads of the 76 Fraunhofer institutes are also university professors, or that they have a chair at a university. And this serves both the Fraunhofer Institute and the university. If we look at it from the Fraunhofer Institute director's point of view, they benefit from this because this association gives them access to basic research. They have access to all of the students, and they can recruit new scientists from the universities. They can recruit interns and undergrads, and they have opportunities for their employees to gain scientific qualifications. Now, looking at it from the same person who is a chair of a university, their affiliation with Fraunhofer opens the door for them to have access to customers, industry-oriented projects. They can put this also into their curriculum, and they have access to all of the facilities that a Fraunhofer Institute has. One very unique aspect of the Fraunhofer Institutes is the Fraunhofer model, the financing model. It's called the 1/3 model. It's made up of 3 pillars. We have base funding, publicly funded projects, and industrial contracts. And these serve very, very unique roles in how a Fraunhofer Institute is set up. The base funding that is received from the government, both federal and state government, 90% from the federal government, 10% from the state government. This enables all of our Fraunhofer Institutes to do very long-term research work, anything from 5 to 10 years down the line. So it's way pre competitive research. The public projects ensure that all of the Fraunhofer Institutes have a very high level of scientific excellence. They have to compete with all other universities, other research organizations. We get our funding from German publicly funded sources and European sources as well. And then the other third is our contractual research, our third-party funding, and this makes sure that we are always delivering service to society through our direct input to the economy. We also do obviously a lot of very international work. Almost everything we do has in some way, shape, or form an international element to it. We have very long-term international affiliation. For example, we have 8 independent Fraunhofer affiliates outside of Germany, including active formal cooperations with 80 countries. And of course, we have representative office and senior advisors also all over the world. I would like to mention, however, one of the Fraunhofer affiliates, because it's one of the areas that I'm in charge of here in Munich, and that is our largest and oldest Fraunhofer affiliate, that's Fraunhofer USA. Currently, Fraunhofer USA has 3 Fraunhofer research centers located in Michigan, Massachusetts, so metropolitan Boston, and then in metropolitan Washington, D.C. and Delaware. We also have 2 offices located in South Carolina and California. I'd just like to mention that to make sure that everyone also on this call knows that we're very active in the U.S. and we also have an affiliate for those of you who would like to reach out to our Fraunhofer entity in the United States. Now, one other thing I'd like to mention was the fact that this Fraunhofer model that I've just presented has attracted a lot of attention. And in fact, around the 2013, 2014, we had many interested U.S. delegates from the Obama administration here in Munich. And they really wanted to learn all about the funding model, the 1/3 model, this university partnership that is shared with our university directors, and because it was their goal at that time to create a similar model in the United States. And I was talking to the organizers of this series before our call, and many of you are probably familiar with the Manufacturing USA Institutes in the United States. And from what I remember, Penny Pritzker and the Obama representatives came to Germany back in 2012 and 13 to really find some of the best practices that worked so well at Fraunhofer. And as far as I know, have incorporated many of those into Manufacturing USA Institutes. So that just on a side note. All right, so now I'd just like to say a few words about how we transfer some of our work into the market. First of all, Fraunhofer has a number of impact goals. At the moment, we have 5 identified main goals. With number 1 is to have a very security and resilient society. That means we want to help all aspects of society kind of identify dangers and risks and to be prepared for them. Affordable healthcare is at the focus, circular economy, a digitized value chain, and clean energy. Now, based on these goals, we cluster the research that is done. We have 76 institutes. Each one is very autonomous. Each has their very own unique R&D profile or portfolio of what they do, but they are clustered into the following research fields: bioeconomy, next generation computing, digital healthcare, AI, hydrogen, resource efficiency and climate technologies, and of course, quantum. We also have something called lead markets. Because Fraunhofer-Gesellschaft is in service of the society at large, we look at what are the markets now and what are the markets in the future, and how can we provide value and service to the entire market. So really looking at a very holistic approach to delivering R&D services, not just in individual products or individual technologies, but seeing, for example, hydrogen. How is this going to affect actual segments of the economy, and addressing our research from that point of view? And these are just some of the lead markets that we're working with right now. Fraunhofer has identified certain ways that we kind of look at our own efficiency in terms of, are we translating what we do into the market? And we look at that by public revenues, and these are our figures from 2020, which we had about roughly 900 million euros. Industrial revenues of roughly 658, international revenues of 276, a large portion of which is in Europe. We had 638 applications for patents. We had 26 spin-offs. Transfer of human resources, I'd just like to say a word about this. The Fraunhofer model, because we work so strongly with universities, we integrate students, master's students, PhD students. We incorporate them into the research work of the individual Fraunhofer Institute. They usually do their academic work there, maybe their PhD there. And the idea behind Fraunhofer is that these educated scientists who understand applied research are going to leave Fraunhofer-Gesellschaft and enter industry or enter the market again, knowing what they know as seasoned Fraunhofer researchers and business people. So the whole concept of Fraunhofer is not to recruit all these people from universities to keep them at Fraunhofer, but they're there to work on research and then go back out into industry and take what they've learned and create more value from it. So we also deliver value to the society through the transfer of human resources. We also have something called the Fraunhofer Academy. We deliver value by training companies through the areas of research that we do. We have specialists in all the areas that I just mentioned in my previous slides. Let's say digitization. Our Fraunhofer Academy goes into companies and trains their companies to incorporate new technologies and be ready for whatever new kind of innovation the company is looking to integrate. So these are just some of our key figures from 2020. Fraunhofer's main area or main customer base are the SMEs in Germany. They make up about 50% of the customers and 30% of the revenues. You can just see some of the names that are listed here on the left. Of course, we feel that they are one of our most important segments because SMEs often do not have the resources to pursue or to have their own research facilities in-house. That's why we partner very, very closely with the SMEs in Germany. That said, we also have a lot of contracts with big companies, meaning 250 to 10,000 employees. This makes up about 30% of our customers and 30% of our revenues, and also large corporations, which make up 20% of our customer base and 40% of our revenues. So we really cover the whole scope. I thought it might be interesting just to give you a very, very, very broad overview of just some of the Fraunhofer technologies that have made a lot of headlines. Fraunhofer research is in so many products and technology and equipment that you get your hands on, but for obvious reasons, it's not put on the product itself. We sell our services to the company that buys it. But some of them that would probably say something to all of the people on the call, very much on the left in the 1990s, the MP3 technology was developed from our Fraunhofer Institute in Erlangen, IIS. As you can see, going up to today, where we're very much involved to today's research areas in quantum and AI and hydrogen technologies. So this is just a very, very broad overview. And to close with my very short introduction on the Fraunhofer Institute, right now there's a lot of talk in Fraunhofer and also in Germany about a lot of the studies that have been done on Fraunhofer and its impact on society. And the latest studies that were done have shown that for about every euro invested in Fraunhofer, the GDP increases by about 21 euros. About 437,000 full-time jobs are created and about 15.2 billion euros are created annually by investments in the economy. These are, I think, very impressive figures. I don't have time to go into too much details about these studies themselves, but if you're interested, I'd be happy to share some of the links in our chat today. So that brings me to the end of my very short overview, and since Paige was so nice to give a very lovely introduction to both myself and Frank, I'm going to just turn over the floor to my esteemed colleague, Frank Henning. Frank.
Thank you, Holly. I hope you can see my screen and you can hear me.
Yes, looks good.
All right. So welcome, ladies and gentlemen, to my contribution to your Lunch and Learn lecture series. I'm really honored to be invited guest speaker at the Georgia Tech Manufacturing Institute. And today I will speak about our holistic, let's say, method, material, and process approach for an efficient product development within the context of applied research with sustainable approach to vehicle lightweighting using composite materials. I have structured my talk, as you can see here, in an introduction, the description of our MMP approach with examples, moving on to questions of sustainability and circularity, and ending with trends and an outlook. Fraunhofer ICT, let me see if I can move this to the next slide. Yeah, Fraunhofer ICT is one out of these 76 institutes that Holly was speaking about, and we are one of the oldest, the seventh in that series, founded in '59. And with about 540 people, we are working here on a campus close to Karlsruhe, which is in the southern part of Germany, close to the French border, and at the northern rim of the Black Forest. Fraunhofer ICT has a large international presence. So our main presence is here, as I said, in Germany, southwestern part of Germany. And we have two partner universities we are working with. We have the University of Western Ontario, as you've heard from a page introduction of my person. I am an adjunct professor there at the university, and I'm heading and managing the Composite Research Center there at Western in London, Ontario. And a similar center is being located in Ulsan, which is in South Korea at the UNIST. So both centers are bridging our activities into markets which are very interesting in order to learn the differences to our European markets, because everybody knows that automotive technologies are global technologies, and if you want to introduce a new technology, it must fit into different markets. And we also know that the automotive industry in North America is a different one than the one in Europe, as well as than the one in Asia, where we have the mega cities, and we have a different size of vehicles available there. So it's very interesting to work with local colleagues on topics of how to apply these technologies and composite materials into applications in the individual markets, together with our teams and partners in these markets. A new Fraunhofer innovation platform has been founded during the pandemic, together with the University of Ostrava in the Czech Republic, where we are focusing on applied artificial intelligence for material development, but also for manufacturing process development. That's in the first phase. Canada is in the third 5-year phase, and Korea has just started the second 5-year phase. Our core competencies are in explosive technology, safety and security. That's the military and defense sector of Fraunhofer ICT. And the other three are mainly dominated by the civil research, which is polymer technology, chemical processes, energy and drivetrain systems. And there are a lot of synergy amongst these areas as well. Today, for example, I want to point out some of the synergies we are living amongst the core competencies, polymer technology and energy and drivetrain system, because we, as being in applied research, and we as engineers, we like to have products to be developed in order to tailor make our materials and processes accordingly. I guess that's a genetic thing for engineers. And so this gives us an excellent platform to work together. Our main headline is sustainability, and I just focused on a couple of topics that we are looking into during these years. Sustainable energy solution, lightweight technologies, which I will mainly talk about today, technologies for recycling and circular economies, powertrain technologies for the future, especially for sustainable mobility applications. So our goal is to develop sustainable technologies in a sustainable way. So what you see here is our windmill. So we're generating our own energy, and this area up at the hill will be covered this year by photovoltaics. And together with these sources, we aim to be at least more than half independent from any type of fossil energy sources. Energy storage devices are becoming increasingly important as a result of the German energy transition. They can compensate for natural fluctuations in solar and in wind energy, and thus convert a renewable energy source into a predictable generating station with uninterrupted supply. They can also make a decisive contribution to grid stability and frequency control, and reduce the need to extend the grid. In the framework of this Redox wind project, a large-scale Redox flow battery storage device has been developed. Let me switch on the pointer. What you can see here, which is located underneath the windmill. And that's connected directly to the intermediate DC circuit of the wind turbine. This unit, consisting of a generator and a battery storage device, has been constructed as a pilot plant at Fraunhofer ICT here at our location in Pinstal. This type of connection between the wind power plant and the battery can ensure self-sufficient electricity supply to isolated applications, companies, or energy-efficient villages. And by the way, quite a bit of composites are being used here as well. Coming back to the focus of today, some examples of products that we co-developed together with our industrial clients. You see here, for example, a lightweight battery module on the left side, where we did the conception and the development of a lightweight traction battery system, which, using innovative design methods and processes, serves as a prototype for the e-mobility of the future. A direct tap cooling of the pouch battery cells is being realized, and a high-performance thermal management system designed to allow for high charging and discharging rates without derating. Another one is here in the center, a very interesting product, the lightweight traction motor, which is a direct cooled electric motor in a composite intensive design for traction applications. The selected cooling concept significantly increases the continuous power density of the motor compared to the state of the art. On the right-hand side, I wouldn't say it's a conventional combustion engine. It's a very special combustion engine that has been developed here. A lightweight internal combustion engine with the aim of that funded research project called LIMOD in the development of a future international combustion engine with a significant reduced mass to improve operating efficiency, thermal management, and reduced noise levels. This is obtained by combining additive manufacturing methods for the metals, as well as large size, lightweight, structural, and functionally integrated composite side covers. The engine concept is optimized for the combustion of non-fossil fuels, such as green hydrogen. That's why I'm saying it's not the conventional kind of combustion, but an interesting alternative to electric-driven vehicles. Let's go one step back. When we talk about lightweighting, we talk about an intrinsic problem that exists, I would say, since the existence of any organic material, because any organic material strives for efficiency, and lightweighting, looking out into the nature, gives us the best concepts and ideas when we talk about lightweight products, also called bionic technology or bionic design. For us engineers, we always try to find a definition for that, what we are doing, and we came up with a definition as follows. Lightweight design is the holistic implementation of a development strategy aiming at realized and required function under given technical, economical, ecological, and social constraints through a system of minimum mass while ensuring system reliability. You see the 4 columns of life cycle analysis: technical, economic, ecological, and social, being accompanying it. And I think every engineering solution has to consider these 4 aspects in the product development chain to be sustainable and successful in the end, especially lightweighting. So when you just condense that to a very small sentence, I would say an engineer has to materialize a function, and in our case, sustainably, with a low weight and a low carbon footprint. To do this successfully, it's a pretty interdisciplinary task where you have to look into methods, design methods, simulation methods. You have to understand materials, you have to understand processes. You have to think in systems. You always have to move the boundary conditions of your system to broaden the horizon, to get as conceptual in your approach as possible. You have to understand with what type of materials you can play with and what type of processes are at hand or developed or need to be developed in order to match to the boundary conditions of productivity. And then you have the social and environmental developments that come into play without announcement, right? So we know the discussions about plastics and the environmental impact of today. So lightweight design is a complex engineering product development task that must be based on an increasingly holistic approach if it is to be successful. And this is not just about the materials, it's also about the joining innovations. Lightweighting without joining is a lot of trade-off in the end. So we have to consider the system. We're always striving for the improvement of weight-specific properties, of improving the materials and coming with new alloys, new fibers, new resins in order to match this competition. And in an industry called aviation, this has been very, very successful, being implemented in the past decades. So in the last 100 years, we can see how we bent the curve, the trend down to low weight, high efficient airplanes. And if you look on the right-hand side, you see basically the creme de la creme of the engineering materials to be utilized for this. Composites, carbon fiber composites, titanium, aluminum, everything we think it's fantastic if we could use that in automotive as well. But automotive is subject to a different field of tension. In addition, of course, the airplane is most time in the air. The car, especially in pandemic, if I look into my car, it's most time in the parking lot or in the garage. So that determines the business case. The owners of these vehicles are totally different, right? Here in automotive, we have high volume, high cost pressure, increasing safety and efficiency requirements, increasing quality and functional requirements, established technology standards, increasing individualization we have to meet. And then we have all of a sudden new kind of car sharing concepts. We have the e-mobility coming up, where we don't have combustion engines, where probably composites can play a different role. We have a high demand for sustainable lightweight solution, and you name it. And when we look into the last 50 years only, we see that the curve is looking completely opposite from aerospace. Our vehicles are getting heavier and heavier. In all the curves we find in literature, just though the gray one here, the internal combustion engine driven vehicles. And now coming into play the electric driven vehicles, we are adding battery packs, we are adding the engine. I'm not talking about the hybrid vehicles because you have the two drivetrains, plus you have the battery. So you're getting in the end in the same ranges. So it's really another weight jump. It's not a decrease of the weight, it's a significant increase of the weight, which we have to deal with. Cars are getting heavy. The electric-driven cars are getting really heavy, especially when we talk about SUVs. Sometimes you need a set of tires in just only 1 year, just because of this incredible increased weight. So we are, compared to the Golf 1, which I drove when I was a young guy getting my driver's license, we increased the weight of a similar ID3, similar car today in battery-driven, 244%. And from the last generation, the Golf 8, is still a 51% increase. So how can we turn around this spiral of weight increase into a weight decrease, and how can we take the momentum of further decrease the weight by adapting brake system, engine, clutch, etc., and what we need, or battery or electric engine, in order to take advantage of a lighter body in white structure. The answer here is completely different to the field of aerospace, because we have a different boundary condition. Airplanes are designed for stiffness. Cars are being designed for stiffness in crash. You better not crashing with an airplane. So, but the probability of crashing with a vehicle is much higher. So we have repair strategies. We have to take in consideration, even more important, platform strategies. So we have partition lines in the system of designing such a body in white, because some parts of the system have to be utilized for other vehicle models, for example. So I think the different approach here is that multi-material design is the way to go, and this multi-material design is not easy to answer, because it gives a different answer to a luxury segment, to a sportive segment, to a mass-produced vehicle, to a platform segment, etc. And it's our job as engineers to figure out what is the most ecologic, economic, and technical viable way to come up with an engineered solution. And it's not salvation to just come with new materials, because we have a lot of challenges, right? We have here complex joining, we have the delta alpha problematic in terms of thermal expansion, we have complex simulation methods to meet the requirements. And we have to deal with the material separation of the life cycle, because we want to generate circularity in the materials we are using, right? So with the big advantages, there are quite some challenges we have to cope with. I'm focusing today on the material class with the highest lightweight potential, the fiber composites. They show anisotropy, and anisotropy is something beautiful for us as engineers because they can also be designed, already be designed on a material level and not just on the product level. So we have one more degree of freedom to be efficient in weight reduction, which is to be exploited and to be feasibly being processed in large-scale processes. So completely different field from aerospace. Why do we think it's important to look not just on circularity and recycling? Because recycling is just 0.1% of the vehicle CO2 emissions over life cycle. 85% in average, according to this study, is depending on the of the CO2 emission is on the use phase. So as lighter we are in the use phase, as less CO2 we emit. And yes, we have to think about recycling, but we have to do it in a responsible way and not just looking into the recyclability of materials and make decisions based on this. Let's quickly dive into the world of composites, and it's quite challenging in that short period of time. So let me guide you through this slide. My world of composites is divided in two worlds. One is the continuous fiber reinforced polymers, and the other one, the discontinuous fiber reinforced polymers. Those are capable of being draped. Those are capable of being flown. Complex shapes, simple shapes, and as hybrids, beautiful materials to combine with in order to integrate functions and provide structural performance at the same time. The world of these composites can be basically in primary structural application divided and in functional lightweight applications divided. You see here two examples to visualize. Continuous fibers being used in a structural underfloor body structure of a vehicle to incorporate the battery, as well as to provide crash and stiffness to the pedestrian cell from underneath, so the floor module basically. I will highlight that two slides further down my presentation to show you what are the resins being chosen, the manufacturing technologies being chosen, thermoplastic and thermoset, and aluminum in this case as a hybrid solution. Continuous, for these continuous drapeable materials, we have thermoplastic and thermoset resins we distinguish, and what you find in these green boxes are the adequate technologies suitable for producing them in numbers which are relevant for the automotive industry. There are so many more derivatives of these processes, but they are more hand layup and small series production. I was focusing here on large series production. On the right-hand side, this is, for example, the D-mill. That's the internally cooled electric motor, where we have a highly complex housing which integrates the function, enables the intrinsic cooling, enables the heat dissipation at the heat exchanger and not all over the engine. So that's more functional and more complex in shape, and that's why we prefer discontinuous material, which is not of that structural performance, but more on the functional performance. And you see here as well the adequate manufacturing processes, which I don't want to point out in detail because of the time. Just two examples that we developed together or developed with our MMP approach, and therefore I want to quickly introduce the MMP approach prior to that slides. The lightweight design requires not only industry specific, but also product related solutions. So when we look at this holistic approach of getting to the core here, the white box, the lightweight solution, we engineers tend to look at the technical challenge, which is in blue. Then we have the people that look into the economic point of view, that is costs and efficiency, and how can they provide quality to their customers. And then we have the green box, which is again the columns for sustainability and life cycle analysis, ecological boundary conditions, and societal boundary conditions. And I give you one example. When we talk about airplanes, we have a completely different cycle time. We have a completely different size of our product. We have a completely different cost structure, as I mentioned, because we are returning our invest much faster, because we have a higher loading capacity, more passengers that pay their expensive tickets, etc., and it's always in the air. All right. So for this few parts a year, we do a quality assurance by part. In automotive, unaffordable. So in automotive, the quality assurance is in the processes. So in automotive, the processes are the expensive part, and the material needs to be as cheap as possible because that's the volume that runs through. In aerospace, it's exactly the other way around. And it's also very different to the energy field when we talk about windmills. So never let an engineer responsible for aviation design a windmill and vice versa, because either it will be unaffordable or it will be totally over-engineered. And that's why we need to understand these individual markets to get to an appropriate lightweight solution. And by using this boundary conditions to figure out which materials and processes are suitable, we have to develop the methods, and that's what we did with the CAX chain. I will show you in a second, to accompany this optimization process, to narrow the path down to the optimum design for the materials of choice. How does that look like? We are working at Fraunhofer ICT together with our partner KIT, as Holly mentioned. So we have a house of competence that we developed over the past 15 years. All the methods, the virtual process chain, the process simulation, the structure simulation, the optimization, and the KI is being developed with my team at the university side. That's more the basic research on the methods. And then we have the material characterization, which is partly done at the Institute of Advanced Materials at the university, where we do the parameterization of our models and characterize our materials. The process development is done at Fraunhofer, and then obviously we need to disseminate, and that's how we work hand in hand with our partners in our innovation platforms in overseas. Through strategic partnerships, industrial projects, strategic collaborations, one-off industrial development contracts, and also through our spin-outs, like spin-offs, like Simultens, for example, that offers these simulation optimization services on the market to the industry today, including the latest methods. Two examples, utilizing the methods, materials and processes. Here you see these, the subfloor of that Golf kind of vehicle. That was a project that we had with Audi and Volkswagen and a lot of industrial partners along the value chain, where we focused on a car without any steel so that we avoid electrophoretic painting. So that's aluminum, magnesium, and carbon fiber composites and glass fiber reinforced composites. And I want to look into the floor, thermoset, carbon fiber reinforced floor manufactured with pressure controlled RTM, and the rear thermoplastic UD tape overmolded by LFT type of floor. That's molded with tape forming and compression molding. The whole vehicle body in white was achieved a weight reduction against its competitor, an e-Golf here with 153 kilogram, which is quite a number in that body in white segment. The key development was the virtual process chain development, where we developed codes, or we developed algorithms basically to more accurate predict the material. Let's be simple. What the manufacturing, how the manufacturing influences on the material look like. We iterate the geometry and the fiber orientation and the textiles on several simulation steps, do a kind of a virtual design and process optimization, and by doing this, accelerate the design loop to reduce development time and to save resources. So the upper part of that slide stays constant. The lower part is what I want to highlight quickly here. The mold filling is displayed here in the video. So what you see here is a complex preforms that has been assembled with local sandwich structures being incorporated, a simulation that takes into consideration the two-phase air and resin. It takes into consideration fiber draping, fiber volume content, fiber orientation, and therefore we can optimize the injection point. We can prevent air entrapments. We can dry spots. You see here a shot that hasn't been finalized, and we can validate our simulation tools by doing so. So you see here underneath the publications where you can find that in Composite Part A, B, or Composite Structures, some of the results here. For these very fast curing resins that we need in automotive in order to meet the cycle times, we need to modify viscosity measurements in order to measure that viscosity behavior under that short time, because with standard measurement devices, we can get this information extracted. And then we can do predictions, warpage simulation, etc., by a chemomechanical simulation. Same thing with thermoplastics. That's one part out of the mold kind of production of a tape layup, thermoplastic tape layup. You see, it's like ironing a shirt from top to bottom, from inside to the out, in order to avoid wrinkling. So which mold segment needs to close first and which needs to close second in order to drape, because we can't flow that material, it into shape, and then we combine the aluminum together with these continuous fiber reinforced shaped structure by joining it basically with a discontinuous long fiber material that overflows it and flow assembles it, or by overflowing assemble it together to this multi-material kind of solution intrinsically formed. Just the two examples. So we need the methods, we need the material development according to the prediction of the methods, and we need to do the process adjustments. And just if that's considered holistically, we can get to competitive solutions or affordable solutions, let's say. Running out of time, so just want to quickly look into the sustainability aspect as well. So we try to accompany our developments more and more with life cycle assessment from the raw material, the production, the use to the end of life. And a couple of studies have shown that depending on the boundary conditions, we see that the utilization phase is has the most influence on CO2 emissions of the whole life cycle, and therefore lightweighting is an intrinsic challenge which we need to provide solutions for. So hybrid lightweighting can significantly increase product performance and thus decrease the energy consumption. So consequently, it's a key contribution to the CO2 emission. So we need to find, let's say, materials and processes that serve additionally to reducing the weight, also the circularity. Fraunhofer has formed a network to look into this more intensively. What does it mean? We want to close the loop. We want to basically take after use phase the parts back after the dismantling, which is a law in Europe that the car manufacturers have to take the cars back, they have to dismantle it, and we have to make sure that the material is being sorted, it's cleaned, it's collected, it's collected, sorted, cleaned, and reworked, and then either mechanical or chemical recycling, which is to be preferred before we look into downcycling or in general recycling. And that's what we definitely need to avoid, littering or disposing. And so a lot of the research focus at our institute is going into reuse and recycling technologies. And just to conclude that, I wanted to show you three examples. One is a leaf spring that we recycled, where we used highly filled glass fiber reinforced thermoplastics. That is an in situ polymerized ring opening polymerization to polyamide 6, so epsilon caprolactam to polyamide 6 in thermoplastic RTM, where we did mechanical recycling. And with the electric engine housing, which is a thermoset material, where the housing encapsulates electronics, we need to do thermal recycling. So we do a material separation and recovery, and then a matrix pyrolysis or pyrolysis. And last but not least, a very interesting study in the aviation sector, a project called Green Sky, where we did a hybrid seating structure, where Fraunhofer and its partners developed an innovative composite-based seating concept for civil aircrafts, incorporating multi-material design, a high level of functional integration, as well as novel material systems and process development. The final demonstrator is a hybrid seat structure, which does not surpass a maximum weight of 10 kilograms, which is easy to dismantle and owns a high recyclability, at least 90% of the seat weight. In order to achieve this high recyclability, both production processes for the cushion, for the primary structure, and the shell structure is using polyurethane, flame and smoke retardant as their respective resin material, which is an excellent material for chemical recycling. When we look into the LCA of these aircraft seat structures in an airplane, over 8 years of lifetime, including manufacturing, use, and end of life, and we are very, very conservative, like 5% weight savings only, because we haven't optimized the shape. It's like black metal molding. If we would do that, we could get to our predictions even further down in weight, 25% in total. But that calculation has been made basically based on the 5% weight saving. So the environmental footprint of carbon fiber structures of manufacturing and end of life is more than 2 times higher. Basically, the calculation is as follows. When we have average 167 seats in each airplane, we fly typically in average 2 million kilometers per year. The break even is reached after a few months, 313,000 kilometers of flight distance already. So it's very important that we are not doing a design for recycling only, but a design for sustainability. Otherwise, you would mistakenly choose aluminum, like a lot of the solutions are choosing because of a better recyclability. But that's just part of the equation. And in order to point that a bit better, more comprehensively out, because it's also complicated and parameter rich, we have to think about how can we computer aid do a kind of a computer-aided eco-balancing, not just a structural prediction or a manufacturability prediction, but also kind of an eco-balancing to evaluate how much material is lost, how efficient is the process, how much material is being wasted or must be recycled, etc. Just to give a quick outline. And I guess time is almost over, so let me jump through the next 2 slides just for information. They are added in the slide deck. Fraunhofer formed a cluster of excellence called Circular Plastics Economy, where together with other 4 colleagues of mine, all directors of other Fraunhofer institutes that contribute in a holistic way to the circularity of plastics, from polymers to additives and compounds to recycling technologies, which I'm responsible for, the circular logistics and sustainability application and demonstration and business and transformation models. And I don't want to go too much into that detail, but there's circular economy assessment. We are looking into biodegradable polymers, additive second life, secondary raw materials, track and trace of these polymers, product design studies, not for composites yet, unfortunately, but that's on the agenda for the future. So with this, let me summarize what I wanted to convey in this very short time, having the opportunity to speak at your event is, I think lightweight solution was always maybe not that hyped. It has been hyped in the past 10 years, but I don't like hypes because they are over-focused a topic, and we need more consistent time and effort to improve. That's what nature does for millions of years in lightweighting. So I think it will be a topic forever for engineering. It's something we have to improve in all generation of products, with a focus now in future on sustainability, maybe more flexible production system to bring the costs down, and more artificial intelligence and data modeling supported processing, reinforced learning, other stuff that can be applied here to be more efficient, and obviously ongoing with material innovations based on natural and natural-based materials. Fraunhofer is just as strong as their partners are, as Holly already said in the beginning. So we are grateful of having and I just picked a few names of universities and partners we're working with from industry, from academia. But obviously, like all of us, we are highly depending on our sponsors, and that's what Holly basically already said in the beginning, a diversity of federal, provincial, European, international funding that helps us to drive this innovation forward. Thank you for your attention, and I'm open for questions.
Thank you so much, Frank and Holly. Holly, thank you for the wonderful overview of the Fraunhofer-Gesellschaft institutes overall. And thank Frank, I want to thank you very much for a closer look at one of those institutes, the Institute for Chemical Technology, ICT, and more specifically the work you're doing in vehicle lightweighting and composite technologies. And thank you for the great summary. You've already contributed a lot to the field, and it sounds like this field is very ripe for further research for many years to come. And we are short on time, so I will jump right to the questions. Looks like we have several that have been submitted through the Q&A panel. A question for Holly: if a U.S. student was interested in working for Fraunhofer after graduation with a BS, MS, or PhD degree, what would you recommend as their initial steps?
Well, first of all, thank you. We are always looking for more researchers, so please reach out to us. My first step would be identify the institute that would be most relevant to your professional profile and contact them directly. They always have a human resource contact on their website, so just reach out.
Thank you. And we have also an individual at Georgia Tech, David Citron, who has expressed interest in, I think, maybe meeting with you one-on-one. I can share his information with you after the conversation today. So his work is on NDE of GFRP and CFRP using terahertz imaging. So he has a lab at a campus in Metz, France, which is, I guess, maybe not too far away. So I'm happy to facilitate that introduction after our presentation today. We do have another question here. This one is for Frank. Can you elaborate on the Redox flow battery technology and why it is promising for stationary energy storage compared to competing technologies?
Well, frankly, and straightforward answer, no, I can do that in detail because I'm not the expert in the field. I was, let's say, more involved in the fossil contributions, put it like this. That has to be answered by my colleague who is very in depth into the competing technologies and gave a firm statement to that. So I'm happy to get an email, and I will forward it to my colleague to get an appropriate answer. I would just let's say have a few ideas, but I'm not sure if they are firm because I don't know the competing technologies in detail.
Thank you for that. Yes, we'll follow up via email. So I see we are at the end of the hour, and I wanted to let our audience members know if you're interested in rewatching any portions of this broadcast, or if you'd like to invite some of your fellow students, or if you're researchers and want to invite some colleagues of yours who are unable to attend live today, we will be posting a recording of this session on the Georgia Tech Manufacturing Institute website. If you go to the tab for past events, you'll find recordings there. This one will be posted within the next couple days. And I want to invite our audience members to also join us next Monday at noon, where the topic will be emerging workforce development programs at Biomade. And it's an interesting follow-up to today's lecture, because Biomade is one of the newest Manufacturing USA institutes to launch. So built on a similar model to the Fraunhofer Institutes, which we heard about today. So thank you everyone for joining us. Thank you, Frank and Holly, for lending us your time today and all the insights and information on the wonderful work that you're doing. We look forward to continuing the dialogue with you.
Thank you, Paige.
Thank you,
It was
Paige.
a pleasure.
From my side too. Thank you.
Have a good evening your time. Everyone else have a good afternoon.
Yeah. Bye-bye. And don't hesitate to get in touch with us. Yeah.
We won't. Thank you.
Bye-bye.